In this video, I'm going to review some of the basic math concepts that you need to know in my Unit 9, the unit on acids and bases. So we are on day 7 of the research project that you guys are working on. And all the information about what's required on day 7 is right here in Google Classroom. Now, by this point in time, every lab group should have a report posted on Google Classroom and a copy of that report posted on the location that I provided for you guys to do that. See if I can locate that for you quickly. So here's the link right here for first period. You simply click the link. I want to do it like this so I can open up a separate page. And so what this is going to do is open up a folder in Google Drive, and you're simply going to post a copy of the report here. All right? Now, every group is supposed to provide feedback on at least 2 other projects. There's one report for your group, and then everybody in your group has to put comments on 2 other reports. Okay? And I'm going to scroll down to several days ago. And let's see, there were some videos you're supposed to watch. An intro to acids and bases for high school. More intro to acids and bases for high school. And then pH, POH, H+, and OH calculations. Those videos you should have already watched. Okay? If you haven't, you're behind already. Those are going to give you instruction on a lot of what you're going to need for the test in 2 days. Okay? So if you haven't watched that, make sure you do that. There's a video down here on acid-base theories and one on Arrhenius acid theory down here. Okay? And then there are 2, these are kind of like PowerPoint presentations, but they're the Google version, the Google Drive version of that. So when you look at the pH, POH calculations video, these are going to go along with it. So this is comparing pH and POH. And that first lab we did in this unit where we looked at the behavior of weak and strong acids, this kind of covers some of this to try to help you understand what's going on there with those. Okay? Most of what we deal with in here is using the Arrhenius theory of acids and bases. And we won't do any calculations with Bronsted-Lowry, but you kind of need to know generally what Bronsted-Lowry is. And that video covers that for you, okay? Now then, going back again over here, excuse me, there's a presentation for pH, POH, and molar concentrations wheel. So if you open this up and you go to the well, this is just the title page here. I'm trying to get it open up on the second page. Here's the second page of it. And if you look at this, okay, then we can see, let me open up the presentation view. All right, this is going to walk you through how to calculate from any of these values to another. That goes along with the video. Okay, so this is the pH wheel. I call it the pH wheel. If you have the hydrogen ion concentration, and that's the the Arrhenius acid theory using H+, that's what we've been using in here. When you watch the video on Bronsted-Lowry, it covers what this is. Okay? So if you have the hydrogen ion molar concentration, when you put any chemical symbol in brackets, what that means is the molar concentration of whatever's inside. So this symbol here in brackets means the molar concentration of hydrogen ions. So if you know the molar concentration of hydrogen ions, you can calculate the molar concentration of hydroxide ions in that same solution using what's here in this box. Okay? And you have to know what Kw is. Let's see. All right, Kw, you need to know the value for Kw, and I don't guess I have it on this, but it should be on the video. The value of Kw. Kw is a constant. That's what the K stands for, a constant. The value of Kw is 1.00 times 10 to the negative 14 molar squared. 1.00 times 10 to the negative 17 molar squared. See if I can add it in here really quickly for you. So Kw equals 1.00 times 10 to the negative 14 molar squared. See if I can make that size a little bit bigger, make it easier to read. How about that? That looks pretty good. And then we'll try to make All right, so I just added that to it, so you're going to have that on there. Oops. All right, so that's the value of Kw. Now, when you type the capital M for molarity or molar concentration, when you're typing it out in a report, you don't really have to put a line under it. When you're writing it by hand, you have to put a line under it. Okay. So if you're typing a report, and you're saying you want to say something is 1.57 molar, you're just going to use a capital M. You don't have to put it on there when you're typing it out. All right. But when you're writing it by hand, it needs to be done because it's just sometimes hard to tell if you're not real careful about it. All right. So going back to the presentation then, we got this far, and then so if we want to go from hydrogen ion concentration to pH, pH is the negative logarithm, here it is right here, I'm pointing to it, is the negative logarithm of the hydrogen ion concentration. So logarithm on your calculator, go to the computer screen here for you to see this, or the camera for you to see this. It depends on your calculator, and the video walks you through this. On this calculator, logarithm, log logarithm is right here. Okay, different calculators have different ways of setting it up. It's in different places. On this calculator, the logarithm is above my 10x button, 10 to the x power button. So I have to hit Control and then this button to get a logarithm. On this calculator, TI Inspire, it's going to ask you for the base. If you don't enter a base, the base is 10. On a logarithm, most of your calculator is actually calculating for you a base 10 logarithm unless it specifies otherwise. So in a TI Inspire, when you put in a negative logarithm, it's going to ask you what base. It's going to have a parentheses down here. And so the base you're looking for logarithms is always base 10. If your calculator doesn't ask for it, it's just automatically assuming 10, because most logarithms are base 10. So and on TI Inspire, if you don't enter a number there, it's going to assume it's 10 anyway. So then you're going to put in your number for whatever your concentration is, molar concentration of hydrogen ions, and that will give you the pH. Now, there is no unit of measurement for pH because pH is a logarithm, and logarithms are actually exponents. Okay, the reason we say it's a base 10 is because the logarithm is what is right up here. It's an exponent, and so the unit of measurement goes here on the 10, but not on the exponent. So pH, since pH is a logarithm, doesn't have a unit of measurement. All right, so when you write out the pH, you're going to say pH equals and put a number here. All right, you're not going to say that it's. You're not going to say there's a 1.47 pH. That's wrong, because pH doesn't have a unit of measurement. Okay, pH is a logarithm, and that's what the lowercase letter p stands for. It means that lowercase letter p means negative logarithm. The capital H means the hydrogen ion concentration. So going back now to the presentation. So we can find from the hydrogen ion concentration, we can find the pH by doing the negative logarithm of the hydrogen ion concentration. Since pH is a logarithm, then we can undo pH and find the hydrogen ion concentration by putting it as an exponent on 10. Okay? I'm going to walk you through all this in a minute, really quickly. Now, to go from pH to POH, and POH is kind of like the opposite of pH. It's the hydroxide ion concentration, and base power, the ability of something to behave like a base, has everything to do with the concentration of hydroxide. Something acting like an acid has everything to do with the concentration of hydrogen ions. And so the relationship between pH and POH is simply this equation: 14 equals pH plus POH. So all you got to do is plug in the pH value and calculate POH. Or if you have the POH value, you can go the other way, plug in the POH value and find the pH value. And that's just like gas laws, where you just plug in and isolate the unknown. But remember, this is addition, so to find the unknown part of it, you have to subtract. From pH to hydroxide ion concentration, it's the same calculation as over here with pH and hydrogen ion concentration. Okay? Negative logarithm of the hydroxide ion concentration gives you POH. If you have the if you have the POH, you can find the hydroxide ion concentration by using the negative of the POH as an exponent on 10. Okay? So, let's walk through a set of those really quickly, okay, and just see how that works. All right, just as an example, because all this is on the video, and you need to know how to do this. So let's start with just a really quick, easy example here. Let's say I have 0.0525 grams of hydrochloric acid in 4.75 liters of solution. Okay? So, in order to find the molar concentration, this is like the entry point. Let me go back over here to that slide presentation. Look at the thing here. Okay, so what we're going to do is we're going to start out by finding the hydrogen ion molar concentration. We have the information we need for that now. Okay? All right. So if we have 0.0525 grams of HCl, we need to find the moles of that, and for that we've got to have molar mass. Remember molar mass? We did a lot of that with stoichiometry, and we're going to be doing some stoichiometry in a minute too. The atomic mass of hydrogen is 1.00794, and chlorine is 35.453. There's one of each of these. So 1.00794 and 35.453. And that gives us 36.46094. Last two digits are resulting from empty slots. We're going to round those off. And we get a molar mass of 36.461 grams of HCl. That's equal to 1 mole of HCl. That gives us the ability to build a conversion unit now from this equality statement. Grams go on the bottom to match the grams on the top here. And 1 mole goes in the top. Okay. We cancel out grams and HCl, and we have moles. Now, I have 4.75 liters, and molar concentration is moles over liters. So all I have to do is to put this over liters. I can take 1 over 4.75 liters of this HCl solution, and when I get done I'll have moles over liters. That's molar concentration. So let's do the math here. 0.0525, and then all these are on the top are ones, so we're just going to go ahead and divide by this first number on the bottom, 36.461, hit enter, and also divide by 4.75, and we've got a molar concentration, 0.000303136. Now your calculator may give you the answer as 3.0316 times 10 to the negative 4. It's the same number. Okay, so don't sweat that. Well, this is moles of HCl over liters of HCl solution. That is molarity. We need to round this to 3 significant digits. So I get 0.000303 molar. There's our symbol, HCl solution. Okay? Now, on our pH wheel, that's this value right here. That's the molar concentration of H+. Okay? And so now we can go either around to the right or around the left to get every other value on here. Okay? Doesn't matter which way we go. So this right here, just to be clear, well, actually this is the molar concentration of HCl. The thing is, HCl is a strong acid. So let's back up just a minute and look at this, the presentation we were looking at earlier, because you need to memorize 4 strong bases and 7 strong acids, and guess what? HCl is on there. Okay? A strong acid is one that dissociates completely. So it breaks up, and so every time we have an HCl unit, you're going to completely break it up. So since HCl breaks up completely in water, the number of moles of HCl, well, let me write it, go back here to the camera. Since HCl breaks up completely in water, when HCl breaks up, every HCl unit is going to produce 1 hydrogen ion unit. Okay? So if I'm looking at this as my acid unit, HCl, and the cap here is H, I have 1 HCl, and then when I get it in water, I've got 1 H+. Okay? Moles are counting numbers. So for every mole of HCl units, I also have moles of hydrogen ion units. So the molar concentration of HCl, since and only since it's a strong and single acid hydrogen ion, it's called a monoprotic acid. It only has 1 hydrogen that comes off. Since it's a strong monoprotic acid, the concentration of hydrogen ions is the same as the concentration of the acid itself. So the concentration of hydrogen ions then is also 0.000303 molar. Okay? So now we've got that corner of the pH wheel. Go back here and look at that. We've got the upper left corner. All right, if I want to find the pH, then I'm going to take the negative logarithm of that. So pH equals the negative logarithm of the hydrogen ion concentration. The negative logarithm then of this number, 0.000303. Negative logarithm, 0.000303. And I get a pH of 3.518557371. Now, there is a completely different rule for rounding logarithms and exponents. We're not going to learn a new rule. We're going to rely, even though it's slightly wrong, we're going to rely on the multiplication division rules. So if I have 3 significant digits here, I'm going to choose 3 significant digits in this answer, which means I'm going to assume then that my pH is 3.56. Okay? All right then. All right, then if I know the pH, and I know that 14.00 is equal to pH plus POH, I can plug in 3.56 for the pH and find the POH by subtracting 3.56 from both sides. What I do to one side, I have to do the other. And that'll give me the pH on this side because that's going to go away. And so 14 minus 3.56 is going to give me 10.44. So that's the POH. If I know the POH, I can find the molar concentration of hydroxide ions, because the molar concentration of hydroxide ions is 10 to the negative POH. Well, I don't need a, I just need an equal sign here. I'm going to plug it in. So we're looking for 10 to the negative 10.44. So you can do this in a lot of different ways on a calculator. Probably the easiest way is to find your up caret symbol. That's this symbol right here above my finger. So 10 to the, now whatever I put in here happens to be an exponent, negative 10.44. And I get 3.6307800548. You need to be very careful to read everything on the screen. This says there's a times 10 to the negative 11. Sometimes it uses the symbol E negative 11 to mean times 10 to the negative 11. So this is times 10 to the negative 11. And since this is the molar concentration of hydroxide ions, this is a unit of molarity. All right, again, we're going to go with the significant digits rules for multiplication and division. And we're going to say that there's 4 significant digits here. And the POH is 3.631 times 10 to the negative 11 molar. Okay, so that is the concentration of the hydroxide ion. All right, so I took you around the pH wheel counterclockwise. Going clockwise, the only difficult part is to find, it really is the KW part of that. So let's look at that. I'm going to go back. We actually started out with a molar concentration of hydrogen ions up here. And let's see how to do that going around just the other way. Since KW is equal to 1.00, whoops, now you can put 3 zeros there, but I didn't write it that way. We'll just make it 2 zeros after the decimal. 1.00 times 10 to the negative 14 molar squared. And KW is also equal to hydrogen ion molar concentration times hydroxide ion molar concentration. Then 1.00 times 10 to the negative 14 molar squared. We know the hydrogen ion concentration was 0.000303 molar times the hydroxide ion concentration. And just like when we're doing gas laws, and particularly Boyle's law, we know that we can get rid of this value on this side by dividing both sides by that. We divide by 0.000303 molar on both sides. Okay. All of this then cancels. We're left with hydroxide ion concentration. And what is molarity squared? What does that mean? What does it mean when you have x squared? Yeah, times itself. So this molarity, when I say molarity squared, that's the same thing as molarity times molarity, right? Well, if I have molarity times molarity over molarity, can I simplify that? One of these cancels, right? So I'm going to cancel out one of these molarities here by just crossing out the 2 and canceling out that. All right? And so when we end up with this, we're going to have a unit of measurement of molarity, and that's what we need for the molar concentration of hydroxide ions. Okay? Now you need to be very careful about how you put this in the calculator. I'm going to put what's on the top here in parentheses and what's on the bottom in parentheses. Okay, so I can divide this all as one big problem. 1.00. Now I'm going to use this double E button because double E means times 10 to some power. Okay, times 10 to the negative 14. So this on my calculator is the same as that number right there. I'm going to close the parentheses and then divide and put the bottom number in parentheses. It equals, and this is the concentration using this method, 3.300330033 times 10 to the negative 11 molar is the concentration of hydroxide ions. And we're going to round this one off to 3 digits here, or actually more for this because I could have put as many zeros as I wanted here. So 3 digits, and we get 3.30 times 10 to the negative 11 molar concentration equals hydroxide ion concentration. All right, so let's compare that to the previous number we calculated going the other way around. All right, so they're not exactly the same. And part of that has to do with we're propagating an error every time we round off, and we round it off like 4 times to get this answer. Plus, we're not rounding following the correct rules for exponents and logarithms. So there's going to be some difference, but it's going to be close. It is still 3 times 10 to the negative 11. So they're close, but not exactly the same number because we are actually propagating an error. And I will take that into account when I grade things, depending on which way you calculate it. As long as your math follows the rules I require in this class, we're fine. Okay? When you get to college, you'll be expected to take care of those things a little bit better. Right now, I'm just trying to get you to round properly. So if you really want a better answer, instead of taking, say, for instance, this number, which we rounded off to calculate POH, we take the unrounded answer to find POH. And so here, instead of taking the rounded off answer, we would take the unrounded answer to calculate the pH, and we get a better number. So if we did that all the way through, we wouldn't have as much of an error when we get to the end. Okay? All right. Now, the other thing, primary math you need to know in this unit is the titration stoichiometry. So if you're doing the titration lab, and as a process of testing an acid, you use, let's say you have, you started out with 20 milliliters of some acid. Now, acids always have hydrogen in the front, and since you're working with an acid and you don't know what acid it is, we're just going to put A on the back for some anion. The anion might be chlorine or bromine or iodine or sulfate or whatever we kind of negatively charged polyatomic or monoatomic ion we want to make an acid. So we can just use that as a general formula for an acid. Okay, we started with that, and let's just say we used 35.45 milliliters of an NaOH solution with a concentration of 0.100 molar. Okay, so you titrated it. You put in 35.45 milliliters to find the equivalence point when you were titrating this acid, and the concentration of this right here was the sodium hydroxide solution you were using to titrate with. This is called your known, or the titrant. If you have this concentration and wait a minute, we can use that. That's fine. I meant 1 molar, but this is fine. So what we want to do is to find what the concentration of the acid is, and you can. This is all the information you need to do that, and I'll show you how that works. Okay. So we're going to start with a known amount. We know the amount of the base solution we used. We used 35.45 milliliters of this NaOH solution. Okay. Well, if I'm dealing in molarities, molarity is in moles per liter. So to make all the math work out right, I really need to change this into liters. Okay. Well, we know that there are 1,000 milliliters in 1 liter. So you have to have an equality statement to justify this conversion unit I'm about to build. Okay, and if I do that, then I'm converting milliliters into liters. So I have liters now of sodium hydroxide solution. I can find the moles of sodium hydroxide solution by using this. The molar concentration means moles per liter. Okay, so 0.100 molar NaOH solution is the same thing as saying 0.100 moles of NaOH in 1 liter of NaOH solution. Well, guess what? I've got liters in the bottom here and moles on the top. I can just plug that in right there. 0.100 moles of NaOH over 1 liter of NaOH solution, and liters cancel. And so does NaOH solution cancel. So now I've got moles of NaOH. How do I get from moles of NaOH to HA? Well, here's how you do it. You've got to have a balanced equation. We need a molar ratio. So we have NaOH reacting with the acid, which we're going to symbolize as HA because we don't know exactly what that anion is in the back. And when you do the reaction, you get Na and some anion, and you get HOH. Oh, HOH. Okay? Well, the relationship here is 1 to 1. Okay? So, 1 mole NaOH and 1 mole of the acid. Moles of NaOH go away. All right. Now we need to know what volume to put on the bottom here, and we'll have molarity. We've got volume. Okay, we're just going to put 1 over 20.0 milliliters of HA solution, but I need to have that in liters, right? All right, well, let's convert it to liters. I've already got the equality statement over here. I want to put milliliters on the top this time, 1,000 milliliters and 1 liter on the bottom. Okay, let's see. I'm canceling out milliliters. Okay, when I'm done, because I've canceled everything but moles of the acid over liters of the acid solution, I've got the molar concentration of the acid. Okay, and this is the stoichiometry for titration. Okay, so let's do the math. So in this titration then, we started with we put in 35.45 milliliters of sodium hydroxide solution. Got it. Multiply that times this. And multiply that times, the only thing left on the top over here is 1,000. Hit enter. Then I'm going to divide by 1,000 here. Enter. And divide by 20. And I get a molar concentration of the acid of 0.17725 moles of HA over liters of HA solution. Let's see, I need to round that to 3 significant digits because I've got 3 digits here. And I get a molar concentration of 0.177 molar concentration of the acid. Okay? So we're just using molar concentration as a conversion unit here. And that's really the only difference between all the other stoichiometry we've done. All right, so this is just solution stoichiometry. Anytime you're doing titration, that's what you got to do. All right, so in this unit, then, there's only really 2 kinds of math you need to know how to do. One is the pH wheel math, and the other is the solution titration stoichiometry. math. Okay, and we've done titration stoichiometry, and the other math is no different than the other math we've done in class before. You know, we've done all this kind of math before. It's just figuring out some things a little bit differently. Now, before I completely stop here, let me find my set of test references, because it's the same as yours. And just a little helpful hint here. If you look on here, you will see. All right, so a couple things here on the test references. If you look down here near the bottom of this page, this is the same page your solubility rules are on and your activity series is on. Notice the definition of pH and pOH are down here. So you don't really have to memorize those. You don't have to memorize the whole pH wheel. You can, it's good to know what's there, but you can always check it here. Also, KW, oh look at that. There's the equation and the value there for you, okay? So you just need to know that when it says 1 times 10 to the negative 14, this 1 here is infinitely significant. You can add as many zeros as you want to after that 1, all right? So a lot of the information you're going to need for the pH calculations are right here, okay? It also tells you that M is molarity. I don't know if it tells you, if it gives you what molarity is moles over liters. I don't think so on here, but you need to know that. We've been doing that enough. You should kind of know that. Okay, so those are some helpful things you can find on your test references that may ease some of your stress about getting ready for the test. All right.